Alright, in this lecture we're going to cover failure theories, starting with the maximum distortion energy theory. Before we do that, here's a quote from Albert Einstein. "The whole of science is nothing more than refinement of everyday thinking." I think that's an important thing for us to realize as we move forward into static failure theories. This is also a good time for me to say that all images come from Norton's Machine Design and Integrated Approach, 4th edition, published by Pearson Education. Before we get going any further, it would be helpful for us to consider two special types of loading. The first one is pure axial tension. And when we have pure axial tension, we only have sigma 1. So sigma 2 is equal to sigma 3, which is equal to 0. The Mohr circle looks like this. So we can see that tau max is equal to sigma 1 over 2. The second condition is pure shear. In this case, tau max is equal to sigma 1, which is also equal to minus sigma 3, and the Mohr circle looks like this. The reason these are two important cases is because these are ways we can actually create experiments. So I can get a small piece of aluminum and of a certain size and put it in pure axial tension and wait till it breaks, stretch it till it breaks, and I'll know when that occurs what the stress states within the beam will be during that time. Alright, so what is it that constitutes a failure? So in ductile materials, we're going to say that failure means that the material has distorted so much it no longer functions. So often we're going to take the yield strength as the point of failure because that's when it begins to distort. In brittle materials, we don't have the ability for it to distort. All of a sudden it just fractures and separates, so we're forced to just use either the ultimate tensile or the ultimate compressive strength as the point of failure. There are lots of theories of failure that people have proposed over the years. I'm going to briefly look at 4 of them. So in the first one, the maximum shear stress theory. Failure occurs when the shear stress exceeds the shear strength. And so we'll decide what the shear strength is by using uniaxial testing. Well, the problem with this one is that it doesn't match the data. Now, this isn't the worst theory in the world to use because this is a conservative theory, which means that whatever I get as when it's going to fail, it turns out that it's actually going to fail. It's going to take more stress to fail than just the maximum shear stress. So that's the first theory. The second one to consider is the maximum strain energy theory. And the idea is that the strain energy determines when it's going to fail. And so you get some uniaxial testing and you figure out the amount of strain energy that caused the uniaxial piece to fail, and then you apply that and say that's the maximum energy that the part can hold. But the problem with this one is, again, it doesn't match the data, so we're going to discard this. Now the next one to consider is the one above it, the maximum normal stress theory. And this theory says failure occurs when the normal stress exceeds the ultimate tensile stress. So again, now we're either doing uniaxial tensile or uniaxial compressive testing. And when this is put into practice, we find that this does match what happens with brittle materials. So we'll consider the maximum normal stress theory as it pertains to brittle materials. Then finally we have the maximum distortion energy, which is also called the von Mises theory. And this theory says that failure occurs when it's not the total amount of strain energy, but the amount of energy that caused distortion. Now we can think about this a little bit. Consider that I'm deforming a volume. If I deform the volume by causing it to change shape, the idea is the energy used to do that doesn't contribute to the failure. But what contributes to the failure is when I use energy to distort the shape into a shape it no longer causes. And this turns out to be valid for ductile materials. So let's take a little deeper look into the maximum distortion energy theory, which is also called the von Mises theory of failure. So the distortion energy says that first we need to understand the amount of strain energy that our parts can contain. And so we learned a while ago now that the energy is equal to the integration under the strain stress curve. And if we're in the plastic region, or if we're in the elastic region, then this is just integrating a triangle. And then we can generalize this for sigma 1, sigma 2, and sigma 3. And then if we recognize that the relationship of stress to strain obeys Hooke's law, we can get a generalized equation for the energy, for the strain energy, as it relates to the principal stresses on a given element. The problem with this is that it includes two portions. This includes both the deformation, the hydrostatic, the changing in the volume, as well as the changing of the shape, the distortion. And so what we need to do is to separate this and say that the total energy is equal to the hydrostatic plus the deformation. Well, how do we go about doing that? Maybe the first step is just to say that all three stresses are composed of stress that causes hydrostatic and stress that causes distortion. Add the three of them together and then combine terms, and we'll get that 3 times, we'll get this equation for the hydrostatic. Now again, what we want to consider is only the hydrostatic. So if we're only considering the hydrostatic, we can cancel everything that has to do with distortion. So we'll understand what the hydrostatic stress is as it relates to our principal stresses. From here, the next step is to say that to plug this hydrostatic stress in to our original energy equation, and now we have the energy for hydrostatic energy. And this combines and simplifies, and now we have this nice formula for what the hydrostatic energy is. So we get into the derivation, now we recognize that if this is what the hydrostatic energy is in terms of principal stresses, so plugging in this equation that relates hydrostatic stress to the principal stresses, and this equation that states what the energy of the hydrostatic stress causes, we can then use that to find our distortion energy. And here's our final distortion energy as it relates to the 3 principal stresses. Starting from this point, we now can look at a part that fails in uniaxial tension, so a 1D case, and we recognize that it's going to fail when sigma 1 is equal to the yield strength. Plug that in, and we can see that the yield strength is equal to this function. Now, this is another starting off point. Well, first let's talk about, so looking at distortion energy in 2D, we can see that it creates an ellipse, an elliptical shape. And so sigma 1 and sigma 3 are related to each other. So now I can look at any state of sigma 1 and sigma 3 combinations, all the way from this state here, which is sigma 1 is equal to a maximum and sigma 3 is equal to 0, all the way to here, sigma 3 is a maximum and sigma 1 is equal to 0, and I can see that there are some states in between, and everything just shows up very well here. In 3D is a little bit more difficult to visualize, but again you can see that there's hydrostatic stress, and orthogonal to the hydrostatic stress is a circle that defines the distortion stress, and the distortion stress shows us, and if you think about each of these cross sections here, each of these 2D cross sections would be elliptical shapes. So if you're a graphical person, this might help you to visualize it. Now, the problem here is we don't really want to design all the way until failure. So this is we understand that this is when the part will fail. But do we really want to push it all the way to failure? And because we typically don't want it to fail, instead of using this equation, we're going to call an effective stress, a von Mises effective stress. And we're going to define it this way, and then we're going to set it equal to the yield strength divided by a safety factor for normal stresses. And there's our definition now for normal stresses. So let's consider another case. And also we can see that this von Mises effective stress, it can be written also in terms of x, y, and z with tau xy. So a 6-state stress instead of having to first reduce it to the 3 principal stresses. So 3 principal stresses or a 6-state stress, the typical tensor. If I consider a 2D pure shear case, remember from the Mohr circle it looks slightly different, and I'm going to say that the yield stress is equal to the 2D case, and since sigma 3 is just minus sigma 1, it turns out that the equation simplifies, and I can get that the maximum shear stress is going to be equal to the yield stress divided by the square root of 3, and we're going to call that the yield shear stress. And we can test this experimentally and find what the yield shear stress is. So now I have another equation for the factor of safety with respect to shear. And this brings me to the statement that in ductile materials, we believe that it's shear that actually causes the fracture. So, as a review, we can find the von Mises stresses by either using principal stresses or by using a particular stress case. And from that, we can find a factor of safety with regard to the yield stress of a material that we tested using uniaxial testing. We also can find the maximum shear by taking sigma 1 minus sigma 3 over 2 and recognizing that there's also a factor of safety we can calculate for the shear stress. So if we're using the distortion energy theory, we want to test both of these cases for our given stress state. And whichever factor of safety is smallest, that's the factor of safety of this element at this time.